We're going to take a look at two new derivative rules today, exponential derivatives and logarithmic derivatives. However, you should be very, very aware of this fact. The exponential derivative we're working with today only works for e to the x, and the logarithmic derivative only works for natural log of x. Lucky for us, e to the x and natural log of x are the type of exponential and logarithmic functions that are going to show up almost all of the time. Check out the exponential derivative rule for e to the x. If my function is e to the x, my derivative is e to the x. You're not seeing things? The derivative is literally the same as the function. That seems too easy. Well, it's not too easy. It's a fact. So let's show you how to apply this very, very easy rule to a couple of examples. If I have y equals 7e to the w, and I want the derivative of equation y that happens to be using variable w, I simply say, okay, if there's a coefficient, that stays. We've talked about that already. So the coefficient stays. That's not even part of my thinking. The derivative of e to the w is e to the w. Weird. This equation will give me the slope of this equation at any point I care about. And one more. Function g equals 4v times e to the v. So I picked this one out to show you that we've got some product rule. So I just rewrote it with the brackets showing product rule. And then I literally just go derivative of the first times the second plus the first times the derivative of the second. And the derivative of e to the v is just e to the v. That's that. Believe it or not, if the function is e to the x, the derivative is e to the x. You can't even screw that one up. Now let's take a look at the rule for logarithmic derivatives, specifically the one that applies to natural log of x. And the natural log of x has a derivative that is 1 over x. I like to say whatever the inner guts is inside of natural log goes in the denominator. So if this said natural log of Pop-Tart, we would have 1 over Pop-Tart. It's that easy. Here's two examples to show it in action. The first example, like I did in the previous examples, I used a coefficient just to reiterate the fact that when you take a derivative, the coefficient just stays. So the coefficient stays, and now my brain looks at the natural log of w. The derivative of natural log of w is 1 over w. So here's my final answer, 5 times 1 over w. If I want to make that a little bit more compact, that's 5 over w. One more example. Function h is natural log of t over 3t squared. This is function h that happens to be using variable t, so its derivative symbol, according to Leibniz, would be dh dt. Then I'm going to simply go through the quotient rule, low d high minus high d low, all over denominator squared. And when I do that, the derivative of the high part, low d high, is 1 over t. So this spot right here is really the only place where that rule came into play. Now this looks like a mess. You may or may not want to straighten it up a little bit before you would use it further, but if you don't need to use it further, you just leave it as is. So that's the story, folks. We've got two relatively easy rules, logarithmic for natural log, exponential for e to the x. Learn them. They're easy.